HVAC 360 is brought to you today by Lefty's Construction Publishing. This week, we are happy to announce a new addition to our periodical lineup. For those hand tool enthusiasts out there, it's called Grinder Magazine. Yes, that's right, cut-off wheels, spark-filled photos, and lessons learned will be some of the things that you can find within the covers. And as a special treat, we're going to kick things off right now and answer some questions that come in live from our Twitter feed. No, this is not a dating magazine. No, we do not have an app in the App Store. What am I wearing? Come on! Oh no. Hey, I think we made a big mistake here. Can you get Lefty on the phone? You're not still recording this. You are. Lefty's Construction Publishing, where quality meets quantity. Hey, what's up? Welcome back. This is episode number 115. Matt Nelson here, your host for HVAC 360, helping you be the best and the brightest in the field of HVAC. Well, how do we do that? We do that weekly by sharing lessons learned from the field and talking with industry experts. But I personally don't stop there. I want to encourage you to double down on your weekly dose of HVAC knowledge by hopping on over to HVAC360.com and joining my growing community of people just like you. Just want to point out that we only have 2 weeks left for the initial enrollment of all the alpha members for HVAC 360 membership site. There's a deep discount at this level, and then we're going to close it at the end of January. So visit the website today and get involved. All right, so what's up for this week? This week I talk with Mark Richards of Emery Mechanical Engineering about phase change materials. Mark had a case study that I read and using this product, and I really wanted to learn more about it. There are some show notes, more show notes than usual this week, so check out the website over at HVAC360.com/115. All right, so that's enough of the intro. Let's cut to the tape with Mark Richards. All right, today we're going to be talking with Mark Richards, who is the CEO of Emery Mechanical Engineering. How you doing today, Mark?
Oh, fine. Thanks, Matt. How are you today?
I am excellent. Thanks for asking. Hey, Mark, can you tell me a little bit about some of your background?
Sure. Yeah, I'm a mechanical engineer and work in the HVAC design field and have since I was a kid. I'm a third generation contractor, first generation mechanical engineer based here in San Diego, California. And I went to school at San Diego State University and graduated in 95 with a bachelor's in mechanical engineering and went to work right in for a consulting engineer. Designing HVAC systems. Since my dad was a mechanical contractor, I grew up making ductwork in the shop, installing that ductwork in the field, and had an affinity for the industry, and so parlayed that into a career, and so worked for a consulting engineer, designing everything from schools to pharmaceutical manufacturing. Some of my first projects were at the San Diego International Airport and designing systems for that. And so great experience with them. That company is still around. They're an EXP company now. I left them to go work for a mechanical contractor and headed up their design build group here in San Diego, Pacific Rim Mechanical. Who's still around, and at the time, Pacific Rim was sold to Encompass Services Group, which back in '99 or so, that was a roll up of a bunch of mechanical contractors across the country that went publicly traded, and at about that time, the rolling blackouts were happening in California, and so we got into cogeneration plants, on-site power, and using the waste heat for various applications, heating and or absorption cooling, and did a lot of work in California and spun that off into a separate Encompass business that focused more on power generation. And unfortunately, that company entirely went bankrupt in 2002. And so at that point, I went to work for an owner operator of a lot of the cogeneration plants that we had designed and built, and help them continue to operate those plants and develop a new plant here in Southern California. And once our work was done there, I've been an independent consulting engineer since, out on my own. My company is Emery Mechanical Engineering. We do MEP design and build of mechanical systems for all types of facilities here in Southern California.
So today we're going to be talking about phase change materials. Can you tell me a little bit about what exactly phase change materials are?
Sure. Yeah. Phase change materials, the layman's analogy I like to use is like blue ice for your building. And for those in the younger crowd that may not know what blue ice is, it's a material that melts and freezes at your application temperature of choice. It's an engineered material, and it's made out of an organic substance, basically the derivative of palm seed oil, with fatty acids mixed in and catalyzed at the factory to melt and freeze for the built environment at what we want our building temperature to be.
All right. So I guess a lot of when you talk about phase changes, there's a lot of heat being absorbed or rejected. It can kind of go both ways. Am I getting that right?
Yeah, indeed. In alignment with the blue ice analogy, you put it in the freezer. It gets very cold. You stick it in your cooler to keep your lunch cold or your drinks cold, and then eventually it warms up. And then you got to put it back in your freezer again. This material works in the same modes, but instead of at freezing like blue ice does, phase change materials for the built environment melt and freeze at a variety of temperatures that we want our buildings to be at. So, for example, most buildings want to be controlled to 72 degrees Fahrenheit, right? So there is a material that has a nominal temperature of 73.4 or 23C. And so, I'll bounce back and forth between C and F, but a lot of these products now on the market are rated in terms of degrees C, and standard offerings are typically in intervals of a few degrees C. So, for example, they have a 20 degrees C material, 23, 25, 28 are the most common for integrating into buildings.
So now I know we're going to be talking about one particular project that you had worked on, but in general, are these phase change materials, are they commercially available right now?
Indeed, yeah. There are a handful of manufacturers here in the United States that manufacture and sell phase change material laden materials for the built environment. And I'm most familiar with a company called Phase Change Energy Solutions, based in Asheboro, North Carolina. And they make a material that's a bio-based phase change material, like I mentioned a little bit before. But there are a variety of blends. Some are salt hydrates, some are paraffin wax based, and then we have the bio-based types of phase change material. And the bio-based has by far gotten the most traction as far as market penetration and actual installs into buildings.
So when we talk about these materials going into a project, how would you describe them to people? What do they look like?
Yes, great question. So, envision ketchup, mustard, mayo packets. Little plastic packets of material inside of these packets. But instead of being cut into the little packets that you're familiar with, imagine them being uncut on a flat sheet, a flexible sheet, anywhere between 12 and up to 24 inches wide, with these little packets of phase change material cast into them. In fact, it's made on the same machine that makes ketchup, mustard, mayo packets. In a food grade and injection type device. So it is actually the phase change energy material is actually food grade. It's halal and kosher certified, ironically, and suitable. I think it was recently approved by the USDA for use in food processing and ag applications.
So you could eat it, is what you're saying, basically.
Actually, my dog ate it. I have a bunch in my garage in a plastic bag, and she got into it because she gets into everything, and she she was no worse for the wearing. And it, it's an oil. It very much looks like coconut oil, and behaves a lot like it because coconut oil does melt essentially or near room temperature, but the way it looks and feels is very much the same.
Okay, now you've mentioned two things that throw flags up into in my head, coming from a building science kind of angle. Obviously, you've mentioned plastic, and you've mentioned this is actually biological. So the first thing I got to ask you, this is going into walls, right?
It can go into walls, absolutely.
So I guess what prevents? I mean, are these do they have the right breathability? Are we going to trap moisture in there? Because I mean, if we trap moisture and then mold starts to grow, obviously the food source is right there. Has that been addressed with these phase change materials?
Yeah, great question. So from a material standpoint, the phase change material is inside of an encapsulant. So the material is encapsulated in this plastic jacket. And in some cases, it's got an aluminized foil jacket onto it. But inside the packets, the phase change material is not exposed to the ambient environment. So it communicates thermally through the encapsulation, freezing and thawing. So very much like, your freezer pack, and that analogy of blue ice, the same concept applies there. So from a mold mitigation standpoint, if you have a problem with mold, due to your envelope challenges, this will neither exasperate nor solve an existing issue with vapor transmission and ventilation issues. The encapsulant, or the trade name for the product that Phase Change Energy makes, is called Energy Blanket, and so it's spelled ENRG blanket, and so Energy Blanket stands on its own. So very much like bat insulation, they get stapled up inside of a stud bay. You can also think of the Energy Blanket being installed in the same way.
Okay, so the blanket of itself is more of a what am I trying to say? It allows for moisture passage through it.
Yeah. So unless the edges are taped, it is not intended to be a vapor barrier.
Okay.
It could be, it could be installed in that way, but the intent of integrating into a building is not necessarily meant to be a vapor barrier. Now, however, if that is a concern and you want vapor transmission through it, you can get it such that the encapsulation is perforated in the seams around the packets, so that it could be breathable.
Okay. So now let's focus on this one particular case study that that I brought you on to talk about. Tell me a little bit about why it was done, how you ended up getting involved, and what was it?
Yeah, so thanks for asking. So the case study is known as Thermal Mass 2.0, and it was conceived by Prem Sunharam, who's a global leader of sustainability for DLR Group. And Prem and I had collaborated together on phase change materials. He took an interest on his own time and got some material and tested it to see if it really did what it was supposed to do. And he was intrigued. He built a little test cell and then noodled it over. And Prem's background is engineering and architecture, and a very sustainably minded individual, and saw potential to integrate this kind of material into a building to create thermal mass in a lightweight construction. And so the premise is that phase change material creates a building that behaves like a high thermal mass, high brick, high concrete building, and does it with a building of a lightweight construction with modern metal studs and lightweight exteriors. And so without the cost of the additional structure and mass associated with those types of construction. And so Prem solicited an internal fund within DLR Group. They fund qualified research initiatives to enhance thought leadership and plow new ground for sustainable building technologies. And they happen to be designing a new high school in West Phoenix. It's called Canyon View High School. And so he conceptualized a test because there hadn't been much work done on a large building scale. There have been a lot of data and testing of the efficacy of phase change materials in buildings in much smaller spaces, but nothing in large buildings. And so Prem saw an opportunity there, worked with the Agua Furia school district out there, and convinced them to install it in one of two nearly identical buildings. And so there are two-story, 30,000 square foot classroom buildings, building A or F and B. Building B has phase change material installed in it, and building F does not. And so we also installed a data acquisition system to monitor HVAC energy and compare the two buildings to each other from an energy standpoint. And we also monitored up two classrooms in each building on each floor to look at the surface temperatures and calculate the mean radiant temperatures in those spaces to see thermally how they perform. And so the play for phase change materials in buildings and the value proposition is that it reduces HVAC energy consumption, shifts the peak load out past or into an unoccupied period to be dealt with when ambients are lower, and to increase occupant comfort. And so from a school standpoint, those are in alignment with a lot of their goals to provide, good learning environments for the kids. So fortunately, the district bought off on it. Phase Change Energy Solutions funded the material and my time to go out and design and install the data acquisition system. And so those were commissioned this past August in 18, and now we're through the first semester of data out there.
So now, have you visited the spaces? So just kind of, standing in them, what the F building versus the B building is. Can you notice the difference?
How it is sometimes, Matt, in HVAC land. The perception of people changes from person to person, and so thermal comfort is a fairly nebulous concept. The best analogy that I can give to you is before or during construction, when the material was installed, there was a noticeable difference in the temperature of the building before the building was commissioned. So, in the spring and the summer of 18, we were monitoring temperatures in these spaces before and after the material was installed. And we noted, a 2 to 3 degree difference in temperature between the rooms with PCM and the rooms without, as far as being more comfortable, cooler in general. And so there is a noticeable difference to somebody who can discern a 2 to 3 degree difference when it's 90 some degrees outside. So a better analogy I found was when it was installed at the Easton Archery Center at Olympic Training Center down here in Chula Vista, California. And I went into this building when it was being built. They clad the whole building in it. It was in the roof and the walls. And that's where everybody took their lunch. The construction crews during construction found, it was obvious that building was, much cooler, much more comfortable inside, having the phase change material in it. And so the other analogy I like to give is, radiant sheeting on plywood on roof decks. So when they switched from, regular, OSB or plywood sheeting on roofs to, an impregnated foil radiant barrier, it was obvious that when you worked on that job, you could tell the difference is just actually much cooler under that structure. And so that analogy, I think, holds true with a building with phase change material in it.
So there's different places that you can actually apply this. You said the roof and the walls. I mean, is it like floor to roof deck, or how is it applied in those different situations? It's
so anywhere in the building envelope it can be installed, and the trick is, and we're kind of moving ahead a little bit into the topic about the applications, and my whole goal of getting phase change material into a project is to have it affect thermal comfort and get as much as we can near where the people are in the environment that we care about from a thermal comfort benefit standpoint. And what you find is that the path of least resistance is often up above the ceiling, and especially above T-grid ceiling. And so that gives you a couple of benefits with respect to ease of installation, but also it gets the material closer to the occupants, gives the material the ability to be affected by either passive or active HVAC, such that it can have heat transfer with the product and the environment around it.
Is that ever installed on the interior walls?
Absolutely. Yep. So, phase change material comes in different temperature ratings and BTU capacities. And so dependent upon what you're trying to accomplish, whether it be primarily energy savings or thermal comfort, you can apply it in different locations. And often it's a real estate availability issue, whether it's new construction or retrofit. And so, getting the material into the space where you're able to do it in an economical way kind of really drives the application. And so for new construction, the sky is the limit, right? You can be creative about how to integrate it into the building. But what we found is that it's still a bit of a niche product and not being specified on new construction. And so therefore, most of the applications are retrofit. And so by default, you'll find that it's easier to put it above a drop lid T-grid ceiling as opposed to ripping off drywall, putting it in the walls, and then repairing that drywall.
Fair enough. Okay, so talking about the material, is it more useful? I mean, obviously the case study is in Phoenix, and that's got to be cooling dominant. Nobody's going to argue that. But does it do well in heating modes? I mean, is there a sweet spot for this type of material?
That's a great question. We think that actually for colder climates, it has a greater benefit, simply because the delta T's are more significant in harsher winter conditions. For the most part, trying to keep a space in and around 72 degrees when it's below zero, there's a high delta T, a high potential there. And so, we see that, trying to keep an inside environment comfortable, closer to set point it has a greater bang for your buck, energy wise, in a heating dominated climate. Ironically, now the economic value proposition is opposite, because heat is cheap, right? Using natural gas is much cheaper than using electricity, unless you're using electric heat. So you'll find that the proliferation of the technology has been limited to places where energy cost is high, naturally, and that is in areas that are pretty much cooling dominated. So California, Southern California, and Texas, and then it's heating dominated, obviously, in the northeastern part of the United States. But we're saving BTUs there, as opposed to dollars, except for those who are using electricity for heating.
So now, getting this into your project, how do you explain that to engineers? Is there a lot of engineering calculations that have to go in to the application here, or is it something that is just you're going to get a certain benefit and you can just specify it?
Yeah, it's tricky, because it's a material that goes in the envelope, yet affects HVAC energy, and so you're having to convince an architect that you want to put this product in as a sustainable means of saving HVAC energy, and so it's a bit of a technical sale, and it's an applied engineered product, and so the mechanical engineer needs to get involved to understand what the impact of the phase change materials will be on the HVAC systems. And they are very closely linked and integrated. If not done so, you miss out on the ability to save HVAC energy and make the space much more comfortable. So you have to have a willing participant with the architect, just as much as the client, and a mechanical engineer that is willing to try and quantify the energy savings and the commensurate value proposition, which is not easy.
So I guess, how did the getting this actually installed after the fact? How do the contractors how they perceive this material?
For the most part, contractors are pretty cool with it. They think it's pretty neat, and many times they ask if they can get it installed in their houses. I was involved in a large retrofit project of over 1,000 retail financial buildings all over the United States in 17 and 18, and did a lot of contractor training. And those were retrofits, and the primary mode of integrating the material was to install it above the T-grid ceilings, the T-grid tiles. And so what we found was, it was very low tech to get installed in that application. You literally popped a ceiling tile, laid the blanket out and on top of the vacant tiles. And it worked out to about a 60 or 70% floor area coverage ratio, which worked out to save on the order of 25 to 35% of HVAC energy. So from an install, contractor's perception of it, we got them to a crew of 4 people to install about a 3,000 square foot building in about 3 hours, from setup to install to cleanup. And so it went in very quickly and very easily. So we found that to be a positive experience.
So what were the lessons learned that you had from this project, beyond the energy side, I guess, for the Canyon View project?
Canyon View, the jury is still out. We're collecting data, and it hasn't been fully processed yet. And so we're hoping to see, significant energy savings on the test building compared to the control building. And we'll know a heck of a lot more come August of 19, and we'll have a year's worth of data there. But so far so good. We haven't seen. We're seeing what we want to see. We're seeing lower temperatures, more consistent temperatures in the PCM spaces compared to the other spaces, and that project is unique. The 2-story, 30,000 square foot buildings have different HVAC systems in them. Ironically, the first floor has a 2-pipe fan coil, constant volume fan coil unit per classroom with electric heat and chill water cooling. And then upstairs is kind of a wide open floor plan, big vaulted ceiling with open steel structure. So no ceilings. So the material had to be installed predominantly in the walls. And so that is served by a VAV air handler with electric reheat. And so, each classroom has a VAV box with all exposed ductwork. So the two different types of systems in kind of two different types of construction modes in two different primary locations of the material make it a really nice a test bed for demonstrating the efficacy.
Okay. So, but there weren't any sort of issues with, installing it with, any sort of details getting, need to be adjusted from normal?
No, I mean, the architect would typically provide a wall section detail, showing the sandwich, the metal studs, drywall, insulation, stucco, vapor barrier. And so we showed and worked with them to integrate the phase change material just inboard of the drywall, literally stapled to the face of the studs.
Okay, so there wasn't any sort of conflict between the what you would say the insulation within the stud cavity and the actual phase change material?
No, the thickness of the blanket is only for the lowest BTU content material about 3/8 of an inch thick. At most it'll get to about a half an inch thick. Too much material packed into too much of a thickness, inhibits the heat transfer and the ability for the material to do work for us. So it's not of a high profile. It's a very low profile. The only hazard really is when the guys are putting the drywall on and they're throwing screws in the studs. We want to make sure that they're not hitting the material and the material is leaking out of the packets. And so, therein lies probably our biggest risk with respect to material leaking out of the packets. And so what happens when that happens is, it's basically like a little oil spill. It, may drain the contents of the packet, but at least the bio-based material, when it goes to a full liquid, when it's fully melted, it really only goes to a gel phase. It doesn't get to the consistency of like water. So it's not running out or pouring out. It may just kind of ooze out or stay put. And so, there is risk to having it leach and stain through the drywall in those instances, but it would only be to the extent of the material leaking out of the particular packet that was punctured.
Okay, and at least it's from the outside, you're not necessarily concerned about fasteners coming in through the outside, because you should have enough space there.
Yeah, that's correct. I mean, those are inadvertent punctures, and like you said, yeah, if it's installed in a location, and not behind a drywall wall, then that risk is further mitigated.
Okay. Now, is there? I mean, obviously, what pops into my mind is okay. What if somebody has to in the future retrofit something in that wall? Is there a certain special procedure that they have to follow to make sure that they're not puncturing the thermal phase change material?
Sure, but inevitably somebody's going to nick it and it's going to get punctured. And when that happens, you just drain the packet and put some tape on it. The material is non-toxic. For at least the bio-based materials are non-toxic and are not harmful. And so we haven't had any issues with that per se. It just creates a bit of a mess. So can it be reused if you nick a packet? Yeah, absolutely. Would we recommend, replacing it with another one? Yeah. So, in the grand scheme of things, it's quite inert. There are other phase change materials that are made from salt hydrates that are pretty caustic and corrosive, and that you probably don't want to put in walls at all. So depending upon the type of material you're using, will dictate where it's located.
Okay. So now you said obviously August you have the building up and running, commissioned. Any early data? I know you don't have a full year's worth of data, and you want to wait till August to figure out. But anything that you can tell us right now, or what you expect to happen?
Well, we expect to see between 25 and 35% HVAC energy savings. The data has not been fully processed. We have an issue with a flow meter actually in building B, not reporting its data. So it's not fully reporting everything, unfortunately. So the jury is still out on what the actual data says.
So how does this? How do these materials work? I mean, take me through a day in the life of a phase change material.
Sure. Yeah. So PCM can be engineered to operate for a large range of applications in general. I mean, ranging from minus 50 C all the way up to 175 C. For the built environment, material is made in stock temperatures, and their product that Phase Change Energy Solutions makes is called Energy Blanket, and they specify or manufacture a product based on a Q value, which is its nominal operating temperature at 20 degrees C, 23, 25, 28, and 30. And so these are the standard application temperatures that they offer. And they have three different energy capacities, which they call the M value, which is BTUs per square foot. And so that's kind of like a low, medium, and high amount of material that's cast into the packets on the blanket for different applications. So, in some cases, we can apply a different temperature material into the same blanket, basically make it a hybrid blanket to operate, for a summer and winter application that has two different melt temperatures to deal with those instances, especially for government jobs that have, significantly different summer and winter set point. I think it's like 65 and 78 is pretty big swing. The window in which the phase change material, the bio-based phase change material works, is a pretty narrow window. Its nominal temperature is kind of the midpoint of the curve where the material is a mixture of solid and liquid in its latent range. And so, either side of its nominal temperature, it's got about 2 to 3 degrees C where the material is latent. And when the material is latent, it's doing work for the building. It's either has the capacity to absorb heat or reject heat. So, that latent range of the material is very critical. And so, if the PCM is completely frozen, it only has the ability to absorb heat or melt. And if it's completely melted, it only has the ability to reject heat or freeze. And so this process of melting and freezing of the PCM is the storing and releasing of heat energy. And so the PCM seeks to be at its nominal temperature. So if it's frozen, like in the early morning in the summertime, and is exposed to 2 to 3 degrees above its nominal temperature, it will begin to melt and absorbing heat. But while it's doing this, while it's in its latent phase, it's still at its nominal temperature. That's a straight line on its curve until which it's fully melted, at which point it'll be unable to absorb any more heat and then start eking up in temperature. And so the converse is true for a wintertime scenario. And so, in general, the material works as a thermal battery, absorbing and releasing heat until it's either fully frozen or fully melted, at which point we'll want to either discharge or recharge that thermal battery to work for us again the following day.
All right. So what should engineers know, who want to apply this material? What should they know going into it?
Well, first they need to work with a manufacturer that can provide specific temperature and enthalpy diagrams for their products, done with a calibrated DSC, which stands for a differential scanning calorimeter machine. And what that does is it generates the curve that I just referenced and shows the engineer at what temperatures it melts and at what temperature it freezes, and defines the amount of energy capacity that it will have. And so that's extremely important, being able to get this specific information. Work with a manufacturer that has an applications engineering support capacity. The experience that the engineers at Phase Change Energy Solutions has is extremely valuable, and they exist to support the A&E community with actual field applied lessons learned. Very important. Ask the manufacturer to provide the basics, safety data sheet, technical data sheet, warranty information, installation instructions and documentation, and case studies, specifically associated with your intended application. Solicit references from owners, operators, contractors that have had experience installing the material. Be wary of salt hydrate based materials that are inherently corrosive if punctured. They're also very inexpensive, and the real challenge with salt hydrates is that after 5, 6, 7, 8,000 cycles, that crystalline structure degrades and doesn't always melt and freeze at the same temperature anymore. It kind of shifts, that curve shifts over time. And so, really the cycle, the life cycle of the material and its ability to melt and freeze at a consistent temperature over tens of thousands of cycles is critical to the life of the material. So if you can imagine buying a material that's half the price and works good for 2 or 3 years, nobody really has a vehicle or method for determining if the material is actually working. It's very difficult to, as a user, other than a sophisticated user that's measuring HVAC energy, would know if the material is not melting or freezing at the right temperature anymore. So it's difficult to go back and recommission, because the material is catalyzed from the factory. It's set and it's done. You install it, you forget about it, and unless you get a high quality material out of the gate, it's very difficult to validate if you've got yourself a low quality material that's not working as it should. Consider the physical weight of the material. If installing above T-grid ceilings, the energy blanket product weighs in at about 0.5 pound a square foot, which is within the weight tolerance limit of most T-grid ceilings. I think out of the millions of square feet that have been retrofitted above T-grid, there's yet to be a ceiling tile or a grid failure or issue of sagging. The material is not a boutique product. It must be engineered and in thermal alignment with the intended building operation. Very critical to make sure that the set points of the HVAC systems are in alignment with the nameplate rating of the phase change material. Understand the HVAC energy consumption. If HVAC systems are manually overridden and operated after occupied hours frequently, so the savings goals can be adjusted. So, like every project, once it's dialed in and commissioned, it's very difficult to police rogue activity. If there are energy savings goals, all it takes is a rogue zone, a rogue thermostat, or a manual override to cause the material to stay stuck, frozen or melted, and not do the work that it was designed to do. So recommissioning is important, and by default, when you recommission the HVAC systems to operate according to the sequence, then you'll ensure that the phase change material has a fighting chance to help keep that building comfortable and save energy. Coordinate with the architect the exact locations and quantities for the phase change material, whether the blanket is installed within walls or in the roof assembly or above ceilings. it's critical that the architect shows on his plans, perhaps on the reflected ceiling plan, in many cases, or in details, where the material goes, how much and of what type material is installed where. Very, very, very critical. And so PCM, we want to get it installed close to the occupants to better achieve high comfort levels. We could even go so far as to integrate it within furniture or expose it in cloud type forms directly into the space. Recharging and charging of the material works on basic principles of heat transfer. So, if it's exposed to convective and conductive heat transfer modes, that's better than just conductive. So, if you're burying PCM in a wall cavity with no convection, you're limited to just the conduction path, which may take more time to recharge the material. So those are all really good things. A lot of things that should be considered by the consulting engineer.
So now I got to ask you a couple of follow-up questions to that.
Sure.
Because I guess you bring up good questions as far as was the warranty? What's the length of life that can be expected from this phase change material?
Yeah, great question. So, I know Phase Change Energy Solutions warrants their products out to 10 years. With respect to doing what they in achieving the thermal performance that they publish, and then that's very important when you're integrating a product into a building. You want it to last the life of the building, and so I know the Phase Change Material or Energy Solutions has done material testing to show under multiple thousands, I think on the order of 70 to 80,000 cycles, that the degradation of the melt and freeze curves is less than 5%. So, those kind of analyses are very important. There's a third-party study done by the Army Corps of Engineers that's published and available for public domain that shows life cycle testing, I think only to about 40,000 hours for different types, solid hydrates, bio-based, and paraffin wax, with interesting results that show, in some cases, skewing of some products over time, like I mentioned before on the solid hydrate. So, all very important things to consider when you're integrating this into your building.
So now, if you, I guess, how do you know that it's still, right in its sweet spot? It's still operating how it should. I mean, obviously, it's material that's behind a wall or it's above the ceiling, so you're not necessarily going to know whether it freezes or it's thawed or it's in its gel or frozen state. Is there any way to kind of tell that it's actually performing how it should?
Yeah, you have to take its temperature. So, just like a battery, where they have a percent charge, we can come up with something very analogous by just taking its temperature. And so when you do that, and then you plot that on the manufacturer's curve, a temperature enthalpy curve, you can see where it is, whether it be frozen or melted or somewhere in between. If the material is at its nominal temperature, if it's a Q23 material, and you're measuring, 73.4 degrees, that material is in its latent state. It's somewhere between frozen and melted, which is a good thing. We want our material to be, at its nameplate temperature most of the time. In the mornings, we want it fully frozen. So if it's subcooled and below its nameplate temperature, then we know it's fully frozen. If we know it's 3 or 4 degrees C above its nominal temperature, then we know it's fully melted.
So is that something you could do through the drywall if you had like a thermographic camera or an infrared camera? You could be able to tell that, or do you need to actually measure the material itself?
Yeah, you would have to actually measure the material itself. By default, you could at a high level, look at surface temperatures of a wall if the material is, in direct contact with that. There's just a lag, right? There's a bit of an R value associated with a ceiling tile or a piece of gypboard. Not much. I mean, less than one. But nevertheless, the most accurate way would be to stick a thermocouple or a temperature bulb, inside of one of the packets in various locations and report that to a building management system to give an indication of, in different areas of the building, what is the status of the material. And that's kind of an information only thing. You could use it as a control point to trigger a purge or an active cooling or heating recharge charge mode. So it would be pretty simple to do.
All right. Well, I appreciate you taking the time to talk with us, Mark. And is there anything that you want to leave our listeners with? Any last comments?
Yeah, absolutely. There are a lot of lessons learned that I think we should be aware of, and to those listening, I welcome them to dig into the resources available on what is it? It's phasechange.com. There's a lot of great information at various locations like at NREL, the Department of Energy has some good information on phase change materials. Ben Welter publishes a weekly blast via LinkedIn. There's a LinkedIn user group for phase change energy. Ben's publication, Phase Change Matters, is a great publication on all the developments in the PCM world. But some of the lessons learned I've found is that we want to get phase change material integrated into buildings where we have the ability recharge the material and get it ready for the next day. So we're cooling dominated out here in the southwest part of the world, and we want our material to be frozen. And so a really good way to do that is to use a purge, a natural ventilation purge off peak, to use cool ambient air to flush the building and recharge our material. For the most part, we need a 5 to 10 degree delta T to get the material to release its heat and get frozen for the morning, such that it's ready to absorb heat and melt during the course of the day. And last for hopefully the complete occupied period. Once occupied period is over, the material theoretically is fully melted, and then we have to have a means for rejecting that heat. And so if you can do it passively via natural ventilation, that's great. But in many times, especially in Arizona, you've got to use active mechanical systems because it just doesn't get cool enough outside to do a flush. And so you've got to use traditional HVAC, whether it be blowing cold air into the areas or overcooling the spaces, doing a pre-occupancy cool down to get the material to freeze. Or there's much more innovative solutions like using radiant tubing or a flat aluminum heat exchanger in direct contact with the energy blanket, such that we can directly affect a charge or discharge using medium temperature waters. So I can charge and discharge with as little as say 60 degree water, certainly higher temperature above dew point to prevent condensation, and get my material frozen using cool condenser water and not even chill water. And then let my material absorb the heat from the space and the envelope, and basically render active HVAC moot during much of the day. So there are really some cool active strategies using moderately tempered water and to charge and discharge and get our buildings running passively, and use this material to provide be the primary provider for HVAC, except of course for ventilation. Phase change material only works sensibly. It doesn't do anything, obviously, for moisture and latent. You still have to provide ventilation per code. But for spaces with high sensibles, a lot of great benefits by integrating phase change materials.
Excellent. Well, I appreciate all the information. It's a lot to digest, and if people want to learn more about it, obviously they can reach out to you on LinkedIn or talk to Ben Welter on LinkedIn with Phase Change Matters. So thanks, Mark. Thanks so much for stopping by and giving a chance to talk with us.
Well, I really appreciate the opportunity, Matt, and hope this is of value to your listeners.
All right. Thanks again to Mark Richards for taking the time to chat with us. Check out the show notes for links to things mentioned in their interview. You can find those show notes over at hvac360.com/115. Thanks so much for listening. I hope this is helpful. If you know somebody who's looking for more information on this topic, consider passing this episode along. If you're not a subscriber, consider joining the growing community of people like you over at hvac360.com for some more weekly goodness. And lastly, I would be greatly honored if you consider leaving me a rating in iTunes or Apple Podcasts. And as always, as a standing offer, I'll give you a shout out the following week as soon as I know. So, that's a wrap for this episode of HVAC 360. I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.